Hello everyone, I'm Xiaoqi Chen from Princeton University. Today I will share about my experience of running AES on P4 switches using an optimization technique called Scrambled Lookup tables. To implement secure network application, secure cryptography is necessary. In the security community, there's a famous proverb that goes as follows: never roll your own crypto. You should never invent your own cryptography scheme, as any new invention is likely to be easily broken. Thus, we should standardize cryptography algorithm as much as possible. Well, I came from a measurement background, and in many of my P4 programs, I use CLC32 as the hash function. Sometimes when I was asked how to make my program more secure, I also thought about inventing something based on CLC32. In fact, some other programmers or papers have already done that. It's probably not the safest algorithm you can imagine. Still, I understand why people do that. CLC32 was available in data plan, and we have many other computational constraints that make us afraid of implementing anything else. The data plan has very short pipeline and can only implement very simple arithmetic. So people often worried, is implementing a standardized algorithm still possible at all? Well, I don't really know, so I decided to take a look. In this work, we focus on AES, which is standardized by the National Institute of Standards and Technology, or NIST, and is the most widely used encryption algorithm today. AES is also certified by NSA, or no such agency, for encrypting top secret data for the government. So AES must be really secure. AES is a block cipher, which means it encrypts data one block at a time, and the block size is 16 bytes. If the data is longer than 16 bytes, you have to slice them up and encrypt one block at a time. For this paper, we assume we only have one block. AES uses 10, 12, or 14 encryption rounds, and for one particular round, there are 4 steps: add round key, substitute bytes, shift rows, and mix columns. Now let me introduce each step one by one. In the AES round, at the beginning, you have 16 bytes. We arrange them into a 4x4 matrix. We also have a 16-byte round key. The round key was derived from the encryption key. In fact, in the first round, this is the encryption key. In later rounds, it was derived by calculating a bunch of key derivation functions. We will just do a byte-wise XOR between the round key and the input, and this finished the first step, add round key. After getting the output for the first step, we'll try to do substitute bytes by using a lookup table called the S box, or substitution box. For the value inside the output, for example this one, we'll look it up in the first row and then write the output in the second row to the corresponding location. For another value here, we'll just look it up and then write the output here. So now we get the output after the second step. Let's move on. With the output of the second step, we'll actually color them like this and perform shift rows. So each row is cyclically shifted by 0, 1, 2, or 3 positions. So the first row is put here as is. For the second row, we shift it by 1 positions. Similarly for the other rows as well. After that, we'll finish the last step called mixed columns. We're doing polynomial multiplication in the algebraic field. So this part of the column becomes the parameters for this polynomial, and after the multiplication, we write down the new factors here as the new column. For those of you who don't want to understand the math here, we can skip it. Just make sure we understand that this is a linear operation. So you can also interpret this as a matrix multiplication. So after that, we get a final output. This is output of one round. We can keep going and make this the input for the next round, and just keep doing 10, 12, or 14 rounds. After that, we finish the encryption. I tried to implement AES using P4, and I find it really challenging. There are many existing implementations to optimize AES, but none of them are easy to run on P4 switches. After studying them more closely, I realized these optimizations are designed for embedded systems with different optimization objectives. In particular, in embedded systems, they have very small memory size, so we can't really afford to use a lot of large lookup tables. You have to be very careful when using 4 kilobytes or 8 kilobytes. Also, embedded system use sequential computation. So we just use a bunch of for loops, and hopefully we get a high enough clock frequency to run all the cycles. In P4 switch, it's a different story. First of all, we have relatively larger memory, because these memory are designed to store very large routing tables. Also, data flow in parallel. The most important challenge here is we have a very limited number of stages, so we have to be very efficient in our algorithm in terms of number of stages. So I proposed a solution called Scrambled Lookup tables. It was tailored for P4 switches. Recall that we have a round key, which is a lot of bytes in the encryption key. We'll just look at one particular byte and make it a Scrambled Lookup table. Here, we're given an S box. We try to use the XOR to blend in one XOR into the process. For every individual byte in the encryption key, we implement another Scrambled Lookup table. So here, we have already a lot of tables. We have 16 tables per round, one for each byte in the key. Now, given the input, we'll try to simply use the corresponding table to look up. Here, given this value, we'll look it up in the second row, and we already get the output. We can write it down. Note that we already finished the XOR process, as we are already looking into the 004 value inside the S box. This helps us to skip one XOR in the process. We can also try to fold a few future XORs into the output of the Scrambled Lookup table. So in this way, we use a lot of memory space, as much as 160 times to 224 times of memory space, to save some XORs. This is worthwhile because now every encryption round becomes simpler. Given the input block, we just do one lookup and then do some XORs, and now we immediately get the output block. Theoretically, this only requires 2 hardware pipeline stages per encryption round. In practice, we need 3 or 4 for technical reasons. Each table costs 1 kilobyte of memory. This is justifiable in switches because the switch have very short pipeline and have megabytes of memory. So now let me present some evaluation. First question is, does this algorithm actually fit in the switch? Well, theoretically, every Scrambled Lookup table costs 160 to 224 kilobytes of memory in total. However, in practice, we can't really allocate very small tables. We have some overhead. I try to blend different tables together so we share the overhead. So in practice, we occupy less than 15% of SRAM on the Tofino V1 switch. Other resources are negligible. So, what is the real-world performance then? We implement a prototype on barefoot Tofino switch that performs 2 AES encryptions round per pipeline pass. The prototype requires 4 to 6 recirculations to finish one full encryption. Under the default configuration, Tofino reserves 200 gigabit per second for recirculation. We can encrypt about 10 gigabits per second under this configuration for AES 128. Here we plot in x-axis more and more encryption rounds, and y-axis what's our throughput. As we can see, here on the left-hand side, we're using packet per second as the unit, because we're sending minimum size UDP packets into the prototype, and every packet will carry only one encryption block. On the right-hand side, we'll see the encryption throughput in units of gigabit per second. This is out of context. Let me try to put them back to the context. In our basement, the switch cost $8,000 was lying there. It's only encrypting slightly faster than the laptop in front of me, and the laptop was much cheaper. And also my laptop has some thermal problems. If you use a real computer that's twice as expensive, it's much faster than the Tofino prototype. Well, this is not a quite fair comparison. And the reason is our laptops have dedicated CPU instruction sets for computing AES. And it's there for a reason, because every time we open a web page using SSL or TLS, you're computing AES. So it's worthwhile to have a specialized chip. However, Tofino was a generalized purpose pipeline architecture. So definitely it's much slower. Also, if we block half of the ports and reserve them all for recirculation, we sacrifice some forwarding throughput, but we also get much higher performance. Well, I will just put this number here, and it's not impressive, but each of us will interpret it differently. To conclude my talk, it's indeed possible to run AES on P4 switches. So for security-related data plane applications, we should seriously consider using standardized cryptography. And please, no more CL32. Please avoid hand-roll cryptography. Using the Scrambled Lookup table technique, we save some XOR operations at the cost of using less than megabytes of memory. We can complete 2 AES encryption rounds per pipeline pass, bringing a 122% improvement in throughput, compared with the baseline with only 1 round per pass. There is more room for improvement as well. I believe another 2x to 3x is possible. However, I should also point out that the switch sitting in the basement right now is not the best device to run AES. Your laptop is much faster and power efficient. Still, we need cryptography in data plane. Perhaps we can run other standardized algorithms more easily. Algorithms based on FISO cipher structure should be more friendly to pizza switch lookup tables. Also, we should look into post-quantum cryptographies, such as string learning with errors. One reviewer pointed out that we might use fewer rounds of AES to still achieve good enough security for our network applications. Finally, we should also advocate for dedicated cryptography coprocessors in future, so that our data plane program can easily implement secure crypto on programmable switches. For now, my table-based implementation can be used for backward compatibility. Our P4 code is open source. Please check it out. I will be happy to take any questions. Thank you very much.